Dr. Marek Druzdzel is a professor emeritus in the School of Computing and Information University of Pittsburgh. He holds a faculty appointment in the Computer Science Department in the Białystok University of Technology in Poland. He received his master's in computer science and electrical engineering from the Delft University of Technology in the Netherlands, and his PhD in engineering and public policy from Carnegie Mellon in Pittsburgh. He's a recipient of the Faculty Early Career Development Grant from the National Science Foundation, Outstanding Mentor Award for University of Pittsburgh's Chancellor's Distinguished Teaching Award as well, and 2 Fulbright Fellowships, and so we're Fulbright Fellows here. I've missed that detail before. His research interests focus on probabilistic and decision theoretic methods in decision support systems and human aspects of decision support. And so we are hosting this presentation jointly between the CBTS, that is the Cross-Border Threat Screening and Supply Chain Defense Center, is Centers of Excellence for the Department of Homeland Security, which mission is to focus on technologies detecting biological threats, moving through global supply chains, data integration, and analytics to support threat detection and novel methods to minimize risks to DHS operations. This CBTS center was recently established at TechCNM, and we are leading a project related to COVID-19 in my lab that is making use of Bayesian networks. And I can claim that we're one of the groupies of Dr. Druzdzel's contributions to decision making by the use of what I like to call the transparent side of artificial intelligence, mainly because it's based on the use of probability theory and statistics and the fusion with graphical models. So thank you, Marek, for being here today. As I mentioned before, we have a wide audience that is representing different disciplines across campus. So we're going to have, I guess, an estimated 45 minutes presentation, and then we're going to have the last 15 minutes for questions and answers. So we're very honored to have for having you here, and we're looking forward to hearing your presentation. And I'll ask all attendees if you can turn off your mics and your videos so that we can maximize the efficiency of the presentation. Thank you very much, and welcome remotely, at least, to TechCNM, Mark.
Thank you very much for this generous introduction. I was warned that the audience would be very diverse, so my presentation is going to be quite accessible, I hope, and I'll start from the beginning. A few words of motivation and brief introduction of Bayesian probability theory, Bayesian approach to probability theory, then Bayesian networks, and something that you will not often hear in Bayesian network talks, extended family of graphical models, which it turns out Bayesian networks are related to many things that you already know. Just flashing a few applications, and if there's some time, I will tell you about Bayes Fusion LLC, a startup company that I co-created in 2015, 5 years ago. And we'll play a little with software also, because some of these things are best demonstrated with use of software. So a few words of motivation. There's a beautiful quote from Benjamin Franklin: "In this world, nothing can be said to be certain except for death and taxes." It's a very forceful statement about the world. A lot of things around us are uncertain. If we want to make decisions or support decision making, we need to deal with uncertainty. We need to know how to do it. Another quote that I really like is that of Pierre-Simon Marquis de Laplace. He said something that to many of you will sound ironic. The theory of probabilities is basically only common sense reduced to calculus. the computation. And it's ironic because probability theory is perceived by many people as very hard, counterintuitive. I'll show you this one example of where it is counterintuitive. Bayesian probability theory, it's a different approach to probability. I will explain you the essential difference between the classical and Bayesian view. But I will start with a couple of slides on joint probability distribution. When we talk about random variables in probability theory, we can talk about their distributions. But there's something even more interesting, much more interesting than distribution over a single variable. It's the joint probability distribution over multiple variables. Here is an intuitive illustration where you might have seen that, those of you who have little experience with probability theory. It's a scatter plot showing us values over how values are distributed over two different variables, the one that is on the x-axis and the one that is on the y-axis. Every point corresponds to a combination of values, and this is how they are distributed. We can see that there seems to be some dependence between the two variables. As the first variable takes higher values, the variable represented by the vertical axis tends to also take higher values. And joint distribution is nothing much more than just some probabilistic capturing of relationships between variables in terms of their distributions. Joint distributions are much more interesting than distributions over single variables. And there's a very important reason for that, is that given the value of some of the variables in the joint distribution, you can estimate the probability distributions over the remaining variables. For example, if you have a joint distribution over the amount of work that a student puts into a course, and the grade distribution, joint means that for every student you have the two values. Given that the student tells you that she worked, say, 6 hours a week on the course, you'll be able to very reliably predict the grade coming from the course. And this is the importance of joint distributions. The next thing in the foundations is a formula known as Bayes' theorem. Bayes' theorem, I'll tell you the importance in a moment, but it's a very easy to prove formula. You could do it as a homework assignment. It from the definition of conditional probability, A conditional on B. What is a conditional probability? Essentially, it's a distribution over A if you know that B happened. So conditional on B having happened. The definition is that you look at the joint distribution. Again, you see the thing that I showed you on the previous slide. If you have joint, that can tell you something about the conditional, which is distribution of one given the other. From the definition of conditional probability of A given B and B given A, this is just a formula that is a definition, you can derive the following formula from these two. Probability of A given B, given means if you observe B, what is the probability of A? You have a formula that involves the probability of A before that observation. So the prior probability, a priori probability of A. The formula allows us to derive the posterior distribution, the distribution a posteriori. The brilliance of this very simple theorem, very simple formula, is that it gives us a mechanism for changing our opinion in light of new evidence. The new evidence is B. From our initial estimate of probability of A, given some measures of strength of the connection between A and B, you can derive the probability of A after observing B, which is exactly like the example with the amount of work and the grade distribution. Here's an example that is somewhat outdated, but until I think 1980s, in Pennsylvania, before you got married, you needed to get a license, and to get a license, you needed to undergo a mandatory test for venereal diseases. So here is an example of Bayes' theorem in action. Let the prevalence be very low. These are typically young, very serious people who want to get married. They are generally healthy. 1 in 1,000, say, we assume that, has syphilis. The mandatory test that you need to take is very good parameters, 0.98 sensitivity. Sensitivity means probability of detecting the disease in a sick person, and high specificity, which means the probability of a negative test result in a healthy person. They're both very high. And now imagine your fiancé is coming back with a positive test, and you need to make a judgment. Is she or he, is your fiancé sick? Does the person have syphilis? Bayes' theorem, I use the symbols S for syphilis present, plus for positive test result, gives us a way of calculating this. We have a probability of seeing a positive test result in the population, for which we use a theorem of total probability, a very, very simple formula. I'm not going to dive into that, but it's very, very simple to understand. And then, given that, I substituted the numbers from the exercise, and then substituted the numbers into Bayes' theorem. Here is our a priori probability. Before our fiancé went to take the test, our expectation was 1 in 1,000, just the population expectation. And after calculating, we get the posterior probability, a posteriori, which is around 2%. So the probability that our fiancé with a positive test result has actually syphilis, it's still very low, 0.2. This is the counterintuitiveness of probabilistic inference that I mentioned in the beginning. Let me show you another way of showing that this is a correct calculation, the result is correct. Imagine 10,000 individuals. Every small square corresponds to an individual. The red squares are the sick individuals, 10 in 10,000, which comes down to 1 in 1,000. This is the prevalence. Let us screen all of these people, the whole population. With the sensitivity of 98%, practically all of the sick people will be detected. They will test positive. Specificity is high, which means that 95% of the people who are healthy will test negative, but still there is going to be 5% of false positives. These are the pink squares. So now if all these people, which is roughly 500, a little bit more than that, come back with a positive test result, how many of them have the disease? Roughly 2%, just the 10 out of the 500. You see that we have this formula, gives us the opportunity to change our opinion, and also that probability theory is sometimes counterintuitive to us, to people, which is even more motivation for using it in all problems that require serious thinking. Bayes' theorem and Bayesian statistics date back to 18th century. Reverend Thomas Bayes, an Anglican priest, amateur mathematician, wrote 2 papers. The second paper, the most fundamental, the most known, was published after his death because he wasn't really sure of it, of what he wrote. He published Bayes' theorem in that, and also an interpretation in terms of the posterior, prior and posterior, an ability to change our opinion. And then he hinted that probability could be a measure of our belief, rather than the classical definition of probability, which is limiting frequency in an infinite number of events. If you want to know more about the history of Bayesian statistics, there is an excellent book written 9 years ago by Sharon Burse McGrain. There's a very nice talk that lasts about an hour where she summarizes the most important ideas from the book. Definitely recommend the talk. Bayesian modeling is reliable and it solves hard problems. As you see from the title, you can view the cracking of the Enigma code, hunting down Russian submarines, and finding the French airliner that fell down in 1990s, I believe, in over Atlantic. They also used Bayesian approach to locate the black boxes. You can use both data and expert knowledge to apply this approach. The main difference between the classical view and the Bayesian view is in the meaning of probability, definition of what probability is. Classical statisticians, when they are asked about the probability of nuclear war, for example, typically they will throw up their hands and say, well, we have no clue. It's a limiting frequency. A nuclear war is not a repetitive process. We cannot even imagine that thing to repeat. And Bayesians will have no problems saying 0.24, 0.05, whatever they prefer, whatever they want to say. Because it's a measure of belief, a personal belief. On one hand, it's a mess, of course, because it's subjective. It opens us up to all the mess related to things like everybody is right. In a way, everybody is right in the sense that everybody can have their beliefs. They don't necessarily have to correspond to the truth, but it's beliefs. Classical statisticians, of course, are very suspicious, have been very suspicious, and accuse Bayesians of hocus pocus with priors. How do you know them? Fortunately, Bayesian statisticians have so-called limit theorems, which say essentially that no matter what you start with, as long as the prior is not too weird, you will quickly converge to the distribution that would come from frequencies. So even if you believe that probability of heads in a coin toss is 0.1, if you observe 10 or 20 tosses, you will very quickly get close to 0.5 if you change your mind using your opinion using Bayes' theorem. Of course, there's nothing wrong with starting with frequencies if you have them in the beginning. But even if you don't have frequencies, you can still do useful work because you can start with your beliefs, which opens up a lot of interesting applications that were pretty much closed if you use classical statistics. So these were the foundations. The next thing is Bayesian networks, but also foundations, what they are based on. What is the ingenious, brilliant idea that makes them so interesting and successful in practice? Probabilistic model, whether it's Bayesian network or anything else, encodes the joint probability distribution over variables. And hopefully I have communicated the importance of the joint distribution. It allows us to calculate everything that has to do with those variables, observing some of them, calculating the posterior over the others. You can do anything with joint distribution, and I'll show you a few things that can be done that are really nice. The oldest representation of joint distributions, people were not drawing in their books in 17th, 18th century, but if we draw their verbal explanations, you can imagine a representation of the joint distribution as a tree. Here's the problem that I gave you with the syphilis and screening test. If we have the disease, it has two outcomes, present and absent, so we are drawing a tree.
Marek, we lost your sound. I think you need to turn on your mic again.
Can you hear me now?
Yes, now.
Someone must have muted me. That's all right. I didn't touch anything. Okay, so by the way, let me get that thing, the controls here, so that I can control it. Okay, very good. So I don't know where you lost me, but was it long ago?
It was just a couple of seconds.
Okay, very good. Then I don't need to go back too far.
No.
Okay, so joint distribution essentially is the probability distribution over all combinations of these discrete variables. Two variables, they are binary, 4 combinations. Here are the probabilities of those combinations. Here's another way of writing that. Now, if you have that, you can do a lot of really cool stuff. For example, you can calculate the probability of the disease present. How do you do that? Very easy. Only these 2 branches are compatible with the event that the disease is present. If you add up those 2, you get 0.01, 1 in 1,000, which is what we have. You can do more complex things. For example, what is the probability of the disease present given a positive test result, something that we did using Bayes' theorem. Positive test result makes negative test results impossible, so we throw it out, right? We cut it out. And then we have only 2 elements left. What we need to do is renormalize and then calculate the probability of that branch compatible with the disease divided by all the other possibilities. So that's the formula, just simple calculation on elements of the joint distribution. Simple method, simple modeling approach, but not really very practical. What is the problem? The problem is that trees grow exponentially with the number of variables. If we add 1 more variable, that is binary again, we are doubling the number of branches. Very quickly, we'll outgrow the screen, outgrow the computer memory, and things will become really impractical. With 10 variables, we have 1,000 roughly branches. We just add 1 more variable, it gets 2,000. With 20 variables, we have 1,000,000 parameters that we need. Out of the question for any practical application, and forget about trees. What was the breakthrough thing that made Bayesian networks possible and interesting? The idea of representing independencies among variables in the joint distribution as a way of reducing the number of parameters that you need. 2 brilliant people, a statistician, Philip David, and the computer scientist, Yuda Pearl. It was started by Philip David in 1970s. Yuda Pearl translated that into the world of graphs and brought it to computer science. All brilliant ideas are obvious once you have them, like a wheel. Is the concept of a wheel obvious? It seems too obvious to all of us. We say somebody reinvented the wheel, but it's not obvious at all until you have it. It seems that none of the American civilizations had it. And you can say, well, Incas lived in hilly mountainous area, but many Mayans lived in fairly flat areas. This is a Mayan road on Yucatan, and they didn't have a wheel. They just didn't have it. An obvious idea. What can we do with this brilliant idea of representing independencies? First of all, any distribution that is joint can be written as a product of conditional distributions. This formula is fairly easy to explain. I'm not going to dive into that, but it's just a very simple transformation. A joint can be written as a product of conditionals. We essentially condition on some, then we have to multiply by the joint over this, which we recursively decompose again. Depending on the order that you take these variables, you have essentially n factorial different ways of writing this product. So for 4 variables like here, we have 24 different ways of writing it, depending on the order of these variables. Here, A is first, B, C, D. In this one, we have B, D, A, C, and that's a different factorization. Now, if you have a factorization and have independencies, like these 3 independencies, you can simplify elements, factors in this product. Where do you have these independencies from? Well, you have it from knowledge of the domain of the world. or from data. You can test for independencies in your data. But you can also know things. For example, we probably know that the length of your hair has nothing to do with your intelligence. We know that there's independence. We know it because it might have been tested. We know reading ability and shoe size are very highly dependent on each other, but the dependence disappears if you condition on age. Essentially, small children can't read and have small shoe size. Older children can read and have larger shoes. If you condition on age, the dependence between shoe size and reading ability disappears. So we know that. Knowledge of that can help us reduce the factors, simplify them. If A is independent of C, then A conditional on C will be the same as A. That's the simple rule. Now, Bayesian networks are essentially a graphical representation of A factorization. The way we do it is we essentially draw arcs from all the variables behind the conditioning bar. So A has B, C, and D. Here we are, arcs coming from B, C, and D. D has no conditioning bar, no conditioning variables, no incoming arcs. Very simple drawing of the factorization. So far, no savings. We still need a lot of numbers to represent the distribution. But sometimes when we have independencies and we use them, we simplify the factorization and voila, the graph also simplifies drastically. Absence of an arc is a graphical representation of independencies. So this is the mathematics of Bayesian networks. Not yet very clear, not yet very interesting. Just be patient. We'll get to the interesting stuff in a moment and more intuitive stuff in a moment. So, and probability trees and Bayesian networks, they are doing the same. So they are representing joint distributions, but Bayesian networks are doing it much, much more efficiently. Here is an example. We have a model that I'll show it later in software maybe. It's a diagnostic model for diagnosis of liver disorders. 70 variables. If they are binary, we have 2 to the power of 70 parameters that we would need. That's 10 to the power of 21. But this model has many arcs missing. In fact, 2,400 arcs missing, only 123 arcs present. These missing arcs reduce the number of parameters from 10 to the power of 21 to just 2,000, fewer parameters. In practice, when we are building these models, we take the interpretation of causal influence. So an arc present models causal influence. That's not a very mathematical view. It's more pragmatic, very intuitive, but there are also good reasons for using that view in practice. The mathematics is that graphical models represent independencies, but in practice, we can think about the influences as causal arcs. Here's an impressive example. You can also play with that. If I get the time, I'll show it to you. This model contains 2,100 variables. That's 10 to the power of 632. It's gazillion times more than the number of atoms in the observable universe. That's how many parameters you would need. And this model requires just 12,000 parameters, which is very practical. We can do it. Brief review, Bayesian networks, the structural part, the qualitative part, which mathematically represents independencies, but in practice represents direct influences, causal influences. And the quantitative part are the parameters. The parameters are essentially those elements of the factorization. No parents of the node H, so we have just the probability of H, distribution of H. When there are parents, we have a conditional distribution. If you remember, in the factorization, we had conditional distributions. So there are several distributions depending on the values of the parent. Absence of an arc makes models simpler, also the number of parameters simpler, smaller. What can you do with that? You can observe some of the variables. This is the grounding symbol observation. You can calculate the probability distribution over any variable of interest. In this case, probability distribution of the variable cervix, which is the cervical cancer, different stages of it, after observing positive HPV test result or history of HPV infection and a result of a pap test. That's essentially calculation of conditional probability distribution. You can imagine that as spreading through the network in order to calculate this conditional distribution. And there are algorithms for that that are fairly efficient. And the more sparse the network, the faster the inference is. You can also perform another type of inference. If you have a graph that is causal, you can ask questions involving manipulation. For example, what if we vaccinate a patient? What is the probability of cervical cancer in a vaccinated patient who had a certain result of the pap test? Of course, we have to realize it has to be early enough vaccination, maybe as a child, so that the HPV infection probability of that is zero, close to zero. This type of question is really a question about causal manipulation, intervention from outside. This kind of questions we can ask also. Now, briefly, a review of the extended family of graphical models. Oops. It turns out that something that you have known from starting from your high school probably is that equation-based systems and graphical models are very closely related. Here's a system of 10 equations with 10 unknowns. And we can, usually people call them the proper equations as core equations. And these type of equations for exogenous variables, setting the exogenous variables from outside. These kind of models have been bread and butter in econometrics. In early 20th century, people knew that this kind of models predict the effects of causal manipulation, but only in the 1950s, Herb Simon has shown that you can draw directed graphical models from these equations. You can see intuitively that the variables that are exogenous, they have no incoming errors. The variables that are derived later from the equations have as parents variables that are needed to calculate them, to solve for them. Spreadsheet models, of course, the same. Whenever there's an equation, you can draw an arc from the cell that feeds the equation to the cell that has the equation. It's the same idea, really. Visual spreadsheets. Here's my picture from my favorite, which is Analytica. You can also imagine that as spreadsheet cells that are feeding one another. These are also close relatives of Bayesian networks. From systems of equations, you can construct Bayesian networks that are hybrid, that contain equations or contain continuous and discrete variables and continuous distributions. You can draw dynamic Bayesian networks. You can these are also relatives of Bayesian networks. They include an explicit notion of time. These are relatives of systems of difference equations and further relatives of systems of differential equations. You can use them to derive the probability of probabilities of events as a function of time. As time flows, probabilities. There are also qualitative Bayesian networks that are that have few parameters or order of magnitude parameters. They can also be used to perform useful calculations. I'll show that. There's also an extension of that whole line of business to influence diagrams, to graphical models that support decisions. The additional thing over the Bayesian network that you see here in this part are decision nodes that are modeling explicitly our decisions, our actions that we can perform. And we have also an explicit notion of value, of utility. Special nodes that represent utilities and multi-attribute utility functions also. And then a model like this can directly support decisions. You can calculate the optimal decisions to be made. Graphs can be learned from data. Data can be data mined, and graphs can be learned, both the structure and the parameters. Applications, I'm kind of rushing, but these are really not terribly important things. There are just many. I'll be happy to share the slides with you, whoever is interested. Diagnosis, prediction, prognosis. Those of you who work in artificial intelligence, especially based on data, know that these are different tasks. In Bayesian networks, actually, there is no distinction between them because you can perform inference both in diagnostic direction, but also in the causal direction. It's the same. It's just spreading information across a Bayesian network. Here, the model that I showed you earlier is for diagnosis of liver disorders. Here's another one for prognosis. Prognosis of a therapy for women who came to the hospital for a periodic screening test for cervical cancer. This is a large model with many numerical parameters, but it was learned from data, so not really a terrible limitation to have a complex model with many states. You've seen this model was actually used for diagnosis of diesel locomotives with many possible problems, many possible symptoms. You can embed these methods in websites, in using web interfaces. Here's a favorite that actually is they're one of the clients of Bayes Fusion. Symptomate. You can diagnose yourself. There are complex Bayesian network models under the hood. The web interface asks you questions about your health symptoms and gives you advice on what could be potentially your problem. There are many other diagnostic applications. Again, I'm kind of rushing because it's really superficial, just pointing out things that can be done. Engineering and financial processes using the hybrid, continuous and discrete nodes of Bayesian models, Bayesian network models. Classification, defining which category we are dealing with based on characteristics of an element. That's again the task similar in Bayesian networks to diagnosis and prediction. Detection of spam, fraud, conflicting medicine. Each of these has been approached with by means of Bayesian networks. Recognition. These days, I guess, neural networks, deep neural networks are performing better with massive quantities of data, but Bayesian networks have been used for these tasks as well. Recommender systems, a good application for these. And I'm noticing that I have just 6 minutes left, so let me stop and break here and go to show you some of these things that can be done with Bayesian networks in practice. So here's the software that you can, it's free for academic use. If I have a minute, I will tell you more about Bayes Fusion, the company. The software was developed first at the University of Pittsburgh, and it was at that time free of any charge. With the company, we do charge commercial entities, but it's still free for academics. So anybody with academic affiliation, students and faculty can use it for free for academic research and teaching. Okay, I'm loading a model from our repository, web-based repository. Let me load the diagnostic model. As you remember, this is a representation of the joint probability distribution. It's a Bayesian network. As I make an observation, I'm setting evidence to something. Things have changed, as you see. That observation was propagated. We can use a special interface for that. From this model, we pulled out all the diseases right here, all the possible observations. Here's the one that I made. And if I'm interested in this disease, here is the best thing to do. You can even enter some basic information about the cost of these observations. Sex is a very easy thing to ask, a biological sex. Suppose somebody is female, that apparently gives us a lot of information about this disease. We can perform differential diagnosis. We can ask, what is the best test to distinguish between this among these four things? This is the test that is indicated as the most valuable. As you see, it has shot apart these diseases with PBC, primary biliary cirrhosis, being most likely now. So here's one thing that you can calculate from joint distribution, the value of information based on a measure known as cross entropy. It can be calculated because we have full specification over how these variables are jointly distributed. Let me show you the big model that I presented. You'll see that it's a huge model, but it's a spaghetti of nodes. But updating this model is actually very fast. Let me show you. These are the things that are diseases. I think the blue ones with the target sign. Updating 1, 2, 3. That was a fraction of a second. I pressed when I said 3. Very quick updating in a huge model. There are a few other things I wanted to show you. I wanted to show you dynamic Bayesian networks. Let me open it again from the repository. Here is a practical model that was built by one of my former doctoral students. It's a model of the woman's monthly cycle. Many parameters, but they were learned from a huge data set from a study conducted in Italy. We predict the phase of the monthly cycle based on observations. This is just, so the x-axis is the index of 31 steps. A cycle can last up to 30-something days. If I observe, I'm observing evidence in this dynamic model of bleeding on the first day of the cycle, maybe even on the second if I want to. Please note what happens. The model is capable of predicting when the ovulation will happen. Very simple model, reasoning forward, making predictions over time. This graph is actually very similar to what you see in the medical textbooks on the hormones that are active in the female body during the monthly cycle. Influences of multiple order, first, second, fifth, and 9, apparently enough to learn a model that has very strongly built-in memory in it. I noticed I'm actually out of my allotted time, so let me just do a couple of things, just 2 more things, and then the rest only if there are questions. Learning. There is if you have data, here is data set. I'm dropping it into Genie. Suppose I collected this data set in a bank. Columns are variables, rows are records. They are single customers of the bank. What I can do is I can learn a model very quickly. Within seconds, I have a model that I can use. It's a Bayesian network. I can view as a bar charts. Maybe let me fix the layout left to right. Here we are. Now I can start using this model to make predictions over creditworthiness of an individual. Will the person pay back the loan or not? Based on the data that I observed. I observe some things that I can ask in a loan application form, and I have the posterior probability of will this particular person coming from this population pay back the loan. Not only the insight into the problem, but also a ready-to-use model. Oh, I forgot about one more thing that you can do. If you have joint distribution that I just learned from the data gives me information about the joint distribution. I learned the model. I can look at the thickness of the errors, thickness of the connections. That also gives me interesting insight. Finally, the second thing I wanted to show you is the QGenie, a qualitative type of modeling where we have models. Let this be a simple model. We look at every variable as binary, denoting a proposition. Green means good, red is bad. That's and you can redefine it any way you want. I can perform inference by observing something and looking at the result of that observation in terms of color, the posteriors, on my network. Why we use these models? We can construct them very quickly. There are very few parameters. There is just n plus m parameters, where n is the number of variables, m is the number of arcs. There's one parameter for every arc. You can elicit it by a slider. And there is one parameter for every node. That's it, very quickly constructed. We can now perform calculation, kind of rough order of magnitude. What can we do to influence our target most? Here is one variable. Here it is. This is the one that will influence the profit most. Finally, just one more model that I wanted to show, because I know that you collaborate with Theo Gemelas. There is a model that was developed at Naval War College at the time that he was working there. I was collaborating with him and Brad Hayes. It's a model of stability of a region over 99 variables, variable of interest, civil stability, and again, you can see by the color how things are changing. I should finish now. I'm sorry for rushing. The time is limited. So let me stop now and leave the remaining 11 minutes for any possible questions. We can come back to any of the things that you might be interested in.
Thank you, Marek, for your presentation. You in a record time, you introduced a highly valuable piece of theory, methods, and applications on, as I said before, what I like to cite, the transparent side of artificial intelligence applications that we're lucky to have now available to improve decision making across multiple disciplines. For our group in particular, so the potential to add apples and bananas by using Bayesian networks, bringing multiple disciplines to contribute to improve decision making. This has been an outstanding piece of theory, methods, and our computational applications that we can use to improve decision making. So thank you very much for your presentation. I'll open the floor for questions. So if you like to raise your hand, I can moderate a discussion of any questions that the audience might have. If you would like to post your question as well in the chat box of Teams, please feel free to do it, and I'll try to follow with the questions. There is already a question that was asked, which was, what is the name of the software that was presented? And I think Dr. Heather Manley from CBTS already responded with a link to the software. Any questions?
Oh, no link, but actually, here it is. You can find it from there.
There you go.
I have a question.
Please go ahead.
Yes, so for this kind of statistic, are you asking the questions in the format of yes, no, present, absent? Is it like a two-choice type model?
Great question, because many of the models we saw are indeed discrete, but that's not necessary. What you can do is you can, here is that example of a hybrid model. You can have a combination of discrete and continuous variables. So look, these are discrete, yes, no, spring, summer, fall, winter, but these are continuous variables. So the domain is continuous, and the definition is also an equation that you can equip with continuous distributions if you want to. So the answer is no. You can be more general than just yes, no.
So can you use this in agriculture? I'm trying to think of, I'm an agronomist, and I'm trying to think of how I could use this, and I'm struggling because all your examples are kind of like either medical or, you know, what do you think about? Go ahead.
Yes, I understand. Human mind is very often, our knowledge is domain dependent always. There are no domain independent rules of knowledge. So there are definitely applications in agriculture, and even in the repository, I think there are some agricultural examples. Let's look at large networks. A link, I think it's not agriculture, it's animal farming. What about here? If
And
not,
then,
there
go ahead.
are actually, okay, here it is, barley. Something that has to do with barley.
And then you import your own spreadsheets, and then you tell it to do the whatever calculations you want. Is that typically because my data is collected in the field, I'd put it in a spreadsheet and then import that, I would think.
Yes, you could import it, and then you could try to support learning model from the data. The data format used by the program is very simple. It's a CSV or text, essentially rows and columns, a flat table. You can also ask queries to a database from inside Genie or DBC database. Very simple format, and you can try to analyze your data and learn elements, or maybe the whole network even.
Okay, thank you. Thank you, Marek. Yeah, if you can put that back up or where we get it, I definitely am interested.
Very good. Any other question? There is a question in the chat box from Hank. Do we have to discretize the continuous variables in Bayesian networks? Okay,
no, we don't. We may have to for practical purposes. So as you saw from this hybrid network, you can have both continuous and discrete in the same network. There's no problem. Of course, there are conceptual problems. How do you define conditional continuous distribution? How do you define conditional discrete, conditional or not continuous? But this can be solved. These are conceptual problems. But no, you don't have to discretize. In case of learning, there is a little bit of a problem. When we have a discrete data file, no problem. When we have a continuous data file, let me get an example data file that is continuous actually. Then there is also no problem as long as our data are continuous and follow the multivariate normal distribution. In that case, we can learn a network, a continuous network. In fact, a network that is linear model. So every conditional distribution is actually a linear function, something that is used a lot in social sciences, in psychology, maybe agriculture also, if you can assume linear relationships. So that can be done. The limiting factor here that makes things difficult is that there are no algorithms, no good algorithms for learning from mixtures of continuous and discrete variables. So in learning, that is a little bit of a problem. But representation, not really a problem.
Very good. Any other question from the audience? Anything? Oh, very good. So I have one question for you, Marek. So this is a mathematical formulation, so that is implemented in a computer. And like any mathematical model, it has to go through a process of validation, calibration. So I guess that the same principles of validation, calibration applies to this mathematical model, right?
Yes, correct. So if you suppose you have learned our model from this data, and let me see where that model is. We start closing them because I'm getting. Okay, here's the one that I learned from the data. I can validate it, so I can ask. Here's my original data set. To make things simple, I will just test on the, but you can do cross-validation, leave one out or k-fold. After validation, I did just validation to make it faster. It calculates you the ability to predict the positive and negative credit worthiness. So sensitivity and specificity of this model, accuracy, confusion matrix tells you where the records are, how many of them were correctly predicted. ROC curve for any of these states, and calibration in the sense of the accuracy of the model in giving you the correct probability. So if the model tells you the probability is 0.2, is it really 0.2? The ideal accurate calibration goes from 0, 0 to 1, 1 in a straight line. So the ideal calibration would mean that the model gives you very accurate output probabilities. In AI, people mostly don't do that. It's the probabilistic systems that have this concept of calibration. Used in weather forecast, for example.
I'll take one more question again from Hank. She's asking, do you have any suggestion on deciding the directions and arcs if I'm uncertain about the network structure? For example, when the number of nodes is large.
The direction of arcs. Well, it has to be said that the knowledge engineering for these networks is the bottleneck of the whole business. Assuming that you don't have data, because if you have data, you can do it fairly fast. If you don't have data, then constructing these networks is really the bottleneck. Very laborious, takes a lot of time. And now the questions that you ask is any suggestions about the arcs, which direction, and so. General rule: try to put them in the causal direction. Another rule: don't put too many parents of a single node, because the size of the probability table grows exponentially with the number of parents. These are all combinations of parents. So you see the number of columns grows large. If we add one more arc, you'll double the size of this table. So another rule is not too many parents coming into one node. And then there are tricks for that too. And there are also special distributions known as canonical distributions that will reduce the number of parameters that you need in a node that has many parents. So the question is kind of, it's a good question. The answer would probably take hours, if not days. Just because this is the hardest part of the whole business, constructing this.
Very good. Well, we're arriving to the end of the time we have allocated to this webinar. Marek, we're very pleased and thankful for you making the time to have this presentation here for CVTS and here at Tech CNN. So thank you very much for your presentation, and thank you everyone for attending this webinar. And Marek, you mentioned that you'll be willing to share a copy of your presentation. We have the contact information of all the attendees. So if you don't mind, we can send a copy of the presentation.
Sure, absolutely. I'll be happy to.
Very good. Well, thank you everyone, and have a great afternoon. And Marek, we're going to switch to the second invitation we sent you to have this extended conversation on the CVTS project we have with EHS.
Okay,
Very good. See you there.
See you there.